Well, let's see. Thank you very much, Juan. It's great to be here, and I'm going to give a general talk on going back to early work in condensed matter and recent connections to that have been of interest to string theorists. I see a lot of experts in the audience. I'm a little bit intimidated, but anyway. So before I start, I want to mention this winter school that will be in Jerusalem this winter, just after Christmas, on New Horizons in Quantum Matter. So we have a nice mix of people from condensed matter and also a few particle physicists, Sean Hartnell and Nati Seiberg, and applications are due end of this month. So, okay. All right, so that's my title. I also want to mention a number of collaborators whose work I'll be discussing today. Wenbo Fu and Richard Davison are here, as Yingfei Gu from Stanford, and Andy Lucas, it turns out, just gave a seminar, video seminar in the department on something related now at Stanford, and Avishkar Patel is a current student of mine. So let me begin by some sort of general broad picture on phases of quantum matter. So the ones we generally understand are, let me just call it conventional quantum matter, in which you have essentially the independent electron description being a good starting point. So that would describe, for example, the ground state of a metal, where you fill all the free electron states below the Fermi level. Then when you excite the metal, you get quasi-particles, which are excitations that, roughly speaking, at least in a clean metal, move in a straight line for a long time. But even under this sort of metal, you can think of them as some elementary extended excitations from which you can build all the many particle excitations, at least approximately. So once you have this quasi-particle description, then you're able to describe lots of finite temperature dynamical properties. And one particular property I'm going to focus on is transport. And here's the picture to keep in mind when we talk about quasi-particle transport. You have some excitations which are very dilute at low temperatures, even though the system itself may not be dilute. And these scatter off some impurities, which are these red dots. Okay. A second class of quantum matter, maybe you could call topological quantum matter, which I won't say anything about. So I'll be quick on this one. So here you do still have quasi-particles, but the ground state is no longer just a simple free electron state. There's of course been a huge amount of work on this type of matter. And the new feature of the quasi-particles is that in some cases they can have more exotic quantum numbers, like fractional charge and statistics and so on. So the focus of my talk really is on what I would call quantum matter without quasi-particles, where not only do you have complicated entanglement in the ground state, but you can't think of the low energy excitations in terms of simple particle-like objects that live a long time. And there's a great deal of evidence from experiments in many high temperature superconductors that especially in precisely the density regime where the TC is the highest, is that where it seems as if the metallic state above TC is not amenable to a quasi-particle description. So the picture I want you to keep in mind for transport is this one, where you have a liquid now of excitations, and it's that you can't separate out the individual excitation, and this liquid is going to flow collectively around impurities that you need to put in to understand the experiments. Okay, so what I've done so far is, of course, define a phase of matter by telling you what it's not, and that's never a good idea, because, for example, if I tell you this state doesn't have quasi-particles, you could say, well, you didn't look hard enough. There's some other dual frame, some change of variables where the quasi-particles do exist. And we know examples of that in field theory where that happens, where there's some dual representation where things look free. So you need a way of thinking about systems, if such systems exist, which you can be sure don't have quasi-particles. So one criterion that I talked about some time ago was trying to ask how long does it take the system to equilibrate when you perturb it, or dephase the initial state in some way. Now when you have quasi-particles, basically the operational, the effect of quasi-particles is that it takes them a long time to equilibrate. The quasi-particles live a long time. They have to find each other and collide off each other before things thermalize. So if you look at quasi-particle systems like a Fermi liquid or any system with a gap, you get times that diverge as temperature goes to 0. So then you can ask, is there some shortest possible time in which a system could equilibrate? And a long time ago, I was just thinking in terms of lots of example systems, and that led me to conjecture there's a bound of this type, that this time can never be shorter than a time of order h bar over kt. So this is still a bound with, which is quite strong, because it tells me that if you find a system that where the equilibration time is 1 over square root of temperature, well, that violates the bound. But as far as we know today, there's no such system anybody has found. Now, of course, this idea has been much more precise and semi-rigorous by work of people in the audience. All three of them, I guess, are here. And their contribution was to, first of all, come up with a precise definition of quantum chaos and thermalization using something they call a Lyapunov time. And this has the powerful feature that it's defined not by the long time limit, but some intermediate time limit. And they proved that this Lyapunov time obeys a rigorous bound of this type. Oh, sorry. Okay, well, sorry, I didn't know that. Thank you. Okay. All right. So we can now turn this around and say what I mean by quantum matter without quasi-particles are basically states with the fastest possible many-body chaos. So as an example of the type of system I may want to consider and understand is, say, this high-temperature superconductor with this composition. This is what it looks like. And this is the resistivity as a function of temperature and density. What's plotted is the logarithmic derivative of the resistivity with respect to temperature. And the place where it's black is where this exponent is 2. And so that's what you would identify as a quasi-particle regime. But in here in the middle, you have a resistivity that goes linearly in temperature, which I'm going to refer to, for want of a better name, as a strange metal. Now, I should say I'm not going to present any theory of this strange metal. It's still quite a mystery, but I think some of the ideas that are being developed will really play, in my opinion, an important role in the eventual understanding. Now, there was one very intriguing plot made by Andy McKinsey's group a few years ago, who looked at, now focus only on the red symbols, not the other ones, who computed his estimation of this time tau. Of course, his definition was different from the Lyapunov definition. He interpreted the resistivity using the resistivity. He computed on this axis the value of 1 over tau. And there's a lot of subtleties in converting resistivities to tau, which I'll return to, of course. But modulo those questionable steps, it's still notable that if you take this time tau and many of the strange metals that have been studied, they're all pretty close to this value kt over h bar. Okay, so that's kind of an introduction to why we think quantum chaotic systems are really interesting in condensed matter physics. Here, let me show you a completely different system where you get a very similar time, and of course this is much more familiar to people here. So this is a picture of a famous black hole collision, and I'm not talking about all of this complicated, beautiful stuff that's been observed. I want to focus on the very large stage, what's called the ring down stage of this black hole. So there's a certain ring down time that you can compute from Einstein's equations. And for this particular black hole, that happens to be around 7 milliseconds. And that's really a very tiny part of the, I'm sure it's not what's been observed. So this is a purely classical object in theory of gravity, and you get some ring down time. Okay. Now, black holes, however, are not completely featureless objects, as Hawking taught us. And they also have lots of degrees of freedom, lots of entropy, and a Hawking temperature. And then there's a rather amazing relationship between the ring down time of black hole, a purely classical time in Einstein's equations, and the Hawking temperature. And that's precisely the relation we're discussing, that the ring down time is h bar over roughly kBT Hawking temperature. So this, to a condensed matter physicist, this looks very confusing when you see it, because I thought the ring down time was purely classical. whereas on the right-hand side, talking temperature is quantum mechanical, of course. But of course, h bar cancels out in this particular expression. So Einstein's original expression is correct. But this is the kind of deep relationship that comes out of holography, where classical objects like tau r in general relativity are related to things that are quantum. And that's what's exploited, of course, and very familiar to many people in the audience. All right. So with that general introduction, let me go on to talking about specific systems and their properties. So I'll begin with a quick review of rather old work by many people thinking about model systems which don't have quasi-particles, motivated by these condensed matter experiments. And really the most significant model system is this very basic problem of the Fermi surface coupled to a gauge field. There are many other possible candidates for strange metals, but they essentially reduce in some respect or the other to this basic problem. On the other hand, by using holography, we can try to make a black hole model of a strange metal. And the most popular model has been this Reisner-Nordstrom ADS black hole. I'll say a few things about its properties. They're not exactly the same as this other quantum mechanical system, but you learn a lot by the analogy. Okay, so let me talk about this first. So here's the basic system we'd like to really understand. And there's been a huge amount of work on this for 20 plus years. You start with fermions inside a Fermi surface with certain density, and then you couple them to some, in this case, U1 gauge field. And you're in 2 dimensions. It's a 2-dimensional case that turns out to be the most strongly coupled. So this gauge field is typically an emergent gauge field, meaning it's not electromagnetism. It's something that emerges from the entanglement in the ground state. And it turns out this problem is strongly coupled. You really have to, you can't just do naive perturbation theory in the coupling G. Okay, so this is not the time for me to go through and survey what's known about it. I'll just show a couple of results, one old and one very recent. You can try to ask what is the low energy limit of this theory. And what we understand from a lot of work is that you can encapsulate that low energy limit in a field theory. So now this is a field theory where there's no chemical potential appearing. So you don't have to, when you put the chemical potential, it seems as if you have to worry about very large momenta. So what makes this unfamiliar to quantum field theorists is you have excitation at large momenta but low energy. And this is a theory that has that feature, so it's not obvious how to take the continuum limit. Well, the correct way to take the continuum limit, it appears, is to focus on antipodal points at these 2 large momenta, k0 and minus k0, and expand in powers of momenta about these points. And then when you do it, you get a theory which looks kind of familiar. It's some fermion with some dispersion about k equals 0. They're minimally coupled to A. A is, in this case, the x component of the gauge field. And there's a Maxwell term. So this is something you might call the Gross-Nouveau model. Yeah, I guess so. But in which case, these would be Dirac fermions. But these are not Dirac. They have this anisotropic dispersion, which has a feature that has a line of zeros in momentum space. And that's really what makes it much more complicated than Gross-Nouveau model. So that's a model that people have studied a great deal, and I'll talk about some of its properties. I just want to advertise one very recent result, not yet out, by Avishkar Patel, who's computed this property of quantum chaos in this particular model by looking at this particular 4-point correlation function. And he finds a value in a somewhat uncontrolled calculation because the large n limit is not clearly defined. But if you ignore these 3-loop problems that appear in the large n limit, you get a Lyapunov time, which is larger than the bound by a factor of 2 or so, and also a butterfly velocity, which is defined by how the chaos spreads in space, which goes as t to the 1/3. And interestingly, it turns out in this particular theory, it is a rather subtle feature of the calculation that tau L is independent of n. Okay. Now, on the holographic side, if you're still talking about perfectly clean systems without quasi-particles, as I mentioned earlier, there's this Reisner-Nordstrom geometry where you have a bulk theory which you can take to be to start just the simplest Einstein-Maxwell theory, and that gives you a geometry in which you have your quantum system sitting on the boundary in two-dimensional space, and an emergent holographic direction, which at very low energies is described by an ADS2 near horizon of a planar black brane over here. Okay, so now if you compute various properties of this particular black hole, in particular transport properties, they have similarities, and very suggestive and useful similarities to the Fermi surface in a gauge field problem I just mentioned. But there's one very important difference, which initially used to bother me a lot, but bothers me a little less now, which is that this particular theory doesn't have a Fermi surface. So here you have a compressible state which has a line of zero energy excitation somewhere in high momentum space, and the location of that line of zero energy excitations is constrained by the Luttinger theorem. It has to preserve total volume as constrained by the total charge density, and this particular, and it has various consequences like Friedel oscillations and other things that and for photo emission experiments, but this particular theory on its own doesn't seem to obey any such Luttinger theorem with the Fermi surface. Okay, so what I've argued following work of Tom Faulkner and Nabil Iqbal is that really you need to put non-perturbative quantum gravity corrections involving bulk monopoles to reconstruct the Fermi surface back. And if you really needed to do that, well, then this approach is hopeless. I mean, it's just, you might as well go back to the field theory. But what I think we're starting to appreciate now is as long as you're talking about transport properties, collective properties of the whole system, unlike in normal metals where the Fermi surface is king, everything has to start from the Fermi surface and excitation near the Fermi surface. Those are the things that live long. But here the Fermi surface ultimately doesn't have a special status. It just appears as some oscillation in some higher order correlation functions. It's not identifying any long-lived excitations for you. So maybe it's not that important. Maybe you can really think collectively in terms of the long wavelength excitations of this liquid, which is what holography suggests. And then that whole approach is turning out to be quite successful. But from a condensed matter side, that was really, I think, mentally a big block. I mean, people studying these systems, even without quasi-particles, always began their whole discussion of transport by talking about what's happening near the Fermi surface. And ultimately, perhaps you don't need to do that, at least not as direct a way as you would in the usual Boltzmann theory. So that's the main lesson I learned personally from the whole holographic point of view. And ultimately, it led, I think, to a bunch of new results on the nature of transport in the physical electronic problem. So let me just quickly summarize the kind of results we've got inspired by holography. So the kind of thing you want to measure now is, do this basic experiment where you put in not only a voltage but also a thermal gradient, and you measure the electrical current and the heat current, and this gives you this matrix of electrical and thermoelectric coefficients, and they obey various Onsager relations and so on, but let's not. So we want to compute, so that's the task. If you want to understand the linear resistivity and other things, is to compute this matrix. So if you start with the holographic theory or you start with the Fermi liquid, you can see quite generally that it must have this form. So it has this form where it's got all three of these transport coefficients have a pole at omega equals 0. So the conductivity is infinite. Now, why is that? The reason it's infinite is because these systems are translationally invariant, so there's a conserved momentum. Sometimes people say current is conserved, electrical current is conserved. That's a kind of poor choice of word. It's the charge density that's conserved. The current is not a conserved quantity, even in this system. It's the momentum density which is conserved, but because there's a non-zero overlap between the momentum and the current, that is a state carrying, the most probable state carrying some momentum also carries some current. So that's the kind of thing you can see from holography, but you can also see by hydrodynamics, all the memory functions. And the upshot is by all of these methods, you can precisely fix the coefficient of the pole. It's related to various thermodynamic quantities like the entropy and various correlations in the momentum. Okay, so this, immediately this, so just computing the conductivity of this theory by itself is not very meaningful because it's giving you something that you don't observe. There's some corrections which are also very interesting, but those will be regular and can be computed by both methods and have interesting relations. So what you have to do then is put in some density of impurities, which will relax the momentum. And so really have to think about the system as this collective fluid flowing around impurities rather than quasi-particles that don't live very long scattering off the impurities, which is really what essentially all previous calculations did, even for the non-Fermi liquid. And using that approach, you find that these poles are broadened by some characteristic time tau. And you can get an explicit expression for tau in terms of correlation functions of the theory without the impurities, at least for small density of impurities. And all these expressions agree depending whether you do holography or hydrodynamics or memory functions. And that was a lot of work which took us a while to understand, and especially Andy Lucas played a leading role in that. All right, so now what I want to do is move away from these weakly disordered systems. So if I go back to this plot, you can now understand what bothered me about this plot, or what this plot seems to suggest. So this is telling you that the transport time that you measure from some estimate of the carrier density is basically about a kT over h bar. And I just told you the transport time has nothing to do with chaos, at least in a weakly disordered system. Because of conservation of momentum, this time here, this tau imp, I'm certainly not going to identify that with tau Lyapunov. It's something that depends, that it goes to, if I make the density of impurities very weak, this thing goes to 0. Tau imp becomes infinity. But this is not a system where tau Lyapunov is long. It's still very short. So there's really an issue with just converting resistivity to a time, because resistivity does not measure a time, at least in moderately clean systems. So this has been, a really big puzzle here of how do we get systems where resistivity is related to a time. And what this really tells us is you must study systems with momentum is not at all a good conserved quantity, which naive. So of course, there's been a huge amount of work on strongly disordered system where there's no conserved momentum. But we know, most of the work in condensed matter is that, well, in strong disorder you get localization, many body localization, and lots of other properties. You don't get conduction at strong disorder. At least there's very little theory in that direction. So what we really want to study are systems which are strongly disordered, but still are conducting. And now I think in recent work we're starting to get models of that type. It's really those type of models we need to understand. Is what Sean Hodnall calls an incoherent metal, where momentum, there's no coherent momentum transport, but there still is transport of current and heat. Okay. So that brings me to the second part of my talk, which are these SYK models, which are now starting to give at least some solvable models, not still exactly the ones we want for the experiments, but this, I think there's important progress in getting models of the ones we need to understand strange metals, which are conducting and chaotic but don't have a conserved momentum. Okay. All right, so that brings me to the next part of my talk, which is a bit of a switch and the focus. But you get my sense of the motivation of why I've been worrying about such models for a long time. So the SYK model one can think of as a toy model of a strange metal, and I'll review old and some beautiful new arguments and why it's connected to theory of gravity on anti-de Sitter space. And also this turns out to be a system, as people in the audience showed, which has the fastest possible quantum chaos with exactly this factor 1 over 2 pi. And this is not something I'm going to review, though. Okay, so here's the Hamiltonian in one particular form that's useful for my talk. You have n sites, and on the n sites, you put a density of n times q of spinless fermions. And the most important feature of this Hamiltonian is that there is no single particle hopping. So if you allow a fermion to hop on its own, then this becomes effectively a Fermi liquid, a theory with quasi-particles, described by a random matrix theory with a semicircular density of states and a very long time to chaos, as a recent paper by Ehud Altman, which is not yet out, shows. In fact, it goes at 1 over temperature squared. But if you forbid single particle hopping, then you get much more interesting properties. So in this particular Hamiltonian, you pick any 4 sites, say 3, 5, 7, and 13, and has the feature that a fermion on site 5 and 13 can hop. The 2 fermions can hop together to sites 3 and 7. So every time there's a motion of a fermion, it effectively entangles with some other fermion. So this, you can think of this Hamiltonian as one thing, as a Hamiltonian that maximizes entanglement and has no other potential energy at all. Okay, so one can solve this particular Hamiltonian, and one finds a metallic state. Of course, there's no sense of space, but I'll return to that a bit later. So here there's every point is really as equivalent to every point. And what one finds in this particular model is that the disorder largely self-averages. That is, if I measure some correlation function on site 5, it'll be the same as the one on 2 or any other site. So this is kind of what we need. We need something where you have lots of disorder, where you don't have conserved momentum, but it's not so strong that things fluctuate from point to point when you measure them over any kind of time average. There are other models of this type that we've studied that I won't show, which don't do this. They freeze into a spin glass state. And in fact, when we studied these in the 90s, that's really what we were focusing on, because we were finding it was quite ubiquitous. But this improvement suggested by Alexei has the feature that you can banish the spin glass order really quite easily. And roughly speaking, that's because what the spin glass would want to do is optimize this JIJKL, and the way to optimize this is to find some eigenmode and condense all of the operators, but you can't condense them because they're fermions. If you have a local bosonic operator, then it invariably wants to condense. But here, there's nothing local and bosonic. All right, so that's the beautiful part of it. And now we know also from numerical studies of this kind of model that this is a Hamiltonian which has a strange metal ground state, meaning a state with no quasi-particles, which is also compressible. You can just change the density arbitrarily and smoothly. And that's really a first. I mean, there aren't any other models which are strange metals down to 0 temperature. Here, I mean 0 temperature after you take the n goes to infinity limit. Okay. So the simplest way to see the solution of this model is just to expand in powers of j and just average graph by graph. So this ignores all the subtleties associated with replicas and replica symmetry breaking. There's another model called the SK model that many in the audience I'm sure know. That's the Sherrington-Kirkpatrick model of Ising spins, and that has always at 0 temperature spin glass state. And if you did this for the SK model, you would get the wrong answer. You would get negative entropy, which is what SK found. And then Parisi showed how with replica symmetry breaking, you could cure that problem. And that certainly was very much in our minds and when we looked at this 20 years ago. And so when you do the naive thing, you find, so these equations have a solution. And for almost about 6 months, I didn't believe the solution. There's something wrong. This can't possibly exist. There's a spin glass state that we're missing. Luckily, we just published the paper. But anyway, so the solution of these equations is a very simple-looking equation. But amazingly, these equations have in them so much structure, including knowledge about features of quantum gravity, as we're learning now. Okay. So I'll show you some of those features. So when you solve those equations, you can show generally for this particular model that the correlation functions at 0 temperature decay as 1 over square root of time. But because you can vary the density, the coefficient of the positive time and the negative time need not be the same. So this is kind of a particle hole symmetry. If you had very few particles, and much easier to add particles than to remove particles. On the other hand, if you have almost every side full, then it's much easier to remove particles than to add particles. So the Green's function has to have this asymmetry between increased positive time and negative time. And we parameterize the asymmetry in this peculiar way. This is not the way I parameterized in 93, but I'll parameterize this way because now I'm going to reinterpret very shortly E to be something else. Okay, so if you define it this way, okay, that was the result we obtained in 93. Then, well, this paper was completely ignored for a long time. But then my friends in Paris, Antoine Georges and Olivier Poquelin, started working on it. And they showed that those equations could have also had a nice solution at finite temperature, which was this form. So this asymmetry becomes this exponential in time, and the power law becomes the sine of square root of power law, square root of the sine. And this is exactly the kind of mapping you would expect if there was some conformal invariance in the theory. And this clearly was it's turning out now to be a key observation. Then a year later, working with my friends, we found that the model has an entropy, which I'm going to call it GPS entropy. Okay, good name to remember, at least for this talk. And this was also a really surprise. There's a finite ground state entropy, and this was kind of disheartening because that violates the third law of thermodynamics, and let's just banish the system and not ever worry about it. And it's partly the reason we kind of stopped working on it. We did some more work. There was also the spin glass phases to worry about. We focused on that. But this entropy seemed rather unphysical, although we did realize, especially Antoine and Olivier, that there were a lot of phenomenological features of this model that seemed to match experiments quite well. Okay. Then more recently, after hearing about and learning about holography, and especially the work of Tom Faulkner and David Weig and others, I argue that this system, these are my precise words there, is somehow connected, realizes the physics of near horizon geometries of black holes. And the reason for that proposal was that, first of all of these features here, 1, 2, 3, precisely match the features in holography for any black hole with a near horizon geometry. And in that case, you identify the GPS entropy with the Bekenstein-Hawking entropy. More recently, after Kitaev, Alexei, reawoke interest in this problem, I pointed out that if you now look at how the entropy, this S0, depends on the density of fermions Q, then you can show that this relationship is obeyed, that this E defined here is precisely the E that appears in this thermodynamic quantity. And amazingly, that's also the relation that's obeyed in anti-de Sitter space, where E can be defined in either way. You can do the problem in holography, and you can define E this way, or you can define it this way. It turns out to be the same E, and it's also equal to the electric field on ADS2. So that's now you understand why I'm calling it E, because it's the electric field in ADS2. So the picture here, really, I should have said that it should be, okay, now I'm putting it on a torus. So the idea now is that the low energy physics of the SYK model is very much like this Reisner-Nordstrom solution where your temperature is now so low that the system of finite size, and the whole system just looks like a point. The torus looks like a point, and you just have only time-dependent correlations, and those match in these low energy features that I've discussed to that you would get from this kind of theory. Okay. Now, of course, there's much greater evidence now of this connection, and much sharper and clearer evidence. Sorry, I missed a slide. Okay. So, and that started with the work of Alexei and also Juan and Douglas and others, where you started thinking about fluctuations beyond this saddle point solution. So here you can reformulate the partition function of the SYK model in this way as an integral over two bilocal fields, G and sigma. And they call that because at the saddle point, large N saddle point, they are precisely the G and sigma I introduced earlier, but they depend at that point only on the time differences. but the fluctuations really have to include bilocal fields. You also have to include fluctuations in the replica off diagonal components, and those we studied. I wrote several papers with Nick Reed on that in the 90s for the Ising spin glass, and they are quite important for various properties. So they haven't been looked at here. Most likely they are not very important for any of the properties we are studying. Okay, so now in this form of the action, Alexei and others have noticed that this conformal solution of George and Parcolet has a very simple explanation. And that comes from an action where you ignore these two terms in the effective action. Now, why can you get away with ignoring these two terms? Well, if you go back to this Green's function here, so what you find in this solution, that sigma goes as square root of omega plus mu. So those are the two leading terms. The leading term of sigma has to be mu, and the first correction is square root of omega. So the mu cancels this mu, and the square root of omega is much bigger than I omega. So after that, basically, both of these terms just disappear in the low energy limit, and were not important, at least for many of the properties we discussed. Although they were quite important in some of these results I discussed in the bottom. Anyway, so you can throw those terms out, and then you notice that there's a huge symmetry of this action. There's really, for this particular action, there's two separate symmetries. One is the reparameterization symmetry, where you can just relabel time tau to sigma. And if you make this change of variables, then you find that the action remains invariant, provided you throw these two terms away. And the other is sort of a gauge or local U1 symmetry, where you can just do a phase transformation with this function g, and again you'll find the action is invariant. This is, I'm not assuming that g is an odd or an even function of its argument. It's an arbitrary function of sigma 1 and sigma 2. Okay, so that's one key observation. The other key observation, the structure of these fluctuations, is that the saddle point solutions that we found, which is 1 over square root of time for the Green's function and the sigma, are actually invariant under. So these are not invariant under the full symmetries I just mentioned. For the reparameterization symmetries, they're only invariant under a small subgroup, which is this SL2R subgroup. So this means that when I do fluctuations about the saddle point, I have to account for the fact that such fluctuations are in some sense fake, because they don't make any change to the Green's function. Okay, so those are the key ideas which people in the audience know much more about, and we had a huge discussion on these topics earlier today. But that's, for the general audience, I want to emphasize it's those 2 points that really explain in some deep sense why there's a gravity dual, because these symmetries are precisely the symmetries of gravity. So the reparameterization and gauge invariance are properties of the Einstein-Maxwell theory of gravity and electromagnetism. And if you take a particular vacuum of gravity, which is ADS2, well, the isometries of ADS2 are SL2R. So you have almost exactly the same symmetry structure appearing in these gravity theories, and that's ultimately the reason why we believe that there is a gravity dual beyond just the simple observations so far of the SYK model. Okay, so all right, how am I doing on time? Everyone's very quiet. Any questions? Sorry? Right. So this is just pure ADS2 now, right? Yes. So I'm going to come to that precise question in a few minutes. All right. So what this means is that when we look at fluctuations about the saddle point, there's a line of zero energy modes. There's really 2. One corresponding to F and the other corresponding to G, where the action should be 0 for this particular transformation when F of tau is an SL2R transformation. So with that argument, you can try to write down or derive explicitly from first principles the effective action for these types of fluctuations. And you can think of these fluctuations as basically energy, fluctuation in energy and fluctuation in number density. So this is the kind of action we've got in recent work. This is with Yingfei Gu and Wenbo Fu. So that Schwarzschild action many other people got, that represents the fluctuation of f of tau, basically energy fluctuations. Then this k is, you can think of as the compressibility, that's multiplying d tau phi. And there's a cross term between them, which is again given by the same electric field parameter E. And that's kind of like a thermoelectric effect, connecting number and energy fluctuations. And then from this effective action, you can argue that these coefficients, k, gamma, and E, are related to thermodynamic quantities of the full system. So in particular, k is the compressibility, gamma is the linear copulation with specific heat, modulo this correction, and E has exactly the same definition as before, even from this derivation. It's just the entropy density derivative of the zero temperature entropy. Yes? Well, it's a low order gradient, as is the Schwarzschild action too, isn't it? You can act Schwarzschild squared and things like that, can't you? Well, anyway, so this is a low gradient. Sorry, there certainly could be more powers of derivative here. It's a gradient expansion. Yeah. This I believe is exact. That is, epsilon is related to f in this way, and so that's exactly how it should appear. Okay. So this vanishes at zero temperature, but it's present at finite temperature. It vanishes because the entropy is non-zero. If at zero temperature, if the entropy vanished, then this term would also, not be that important at finite temperature. So it's related to a thermoelectric coefficient again. Anyway, so from this particular action, you can compute, for example, two-point correlation function of energy and charge, and they're just given by the usual thermodynamic quantities that you expect from from the fluctuation dissipation theorem. Okay. All right. So now I want to, so that's to turn to Igor's question. So what I've described so far is a zero-dimensional system, or if you wish, a system of finite size, but the size is so small that the thermal length scale is much larger than the size of the system. So in that case, all you have in the grand canonical ensemble anyway are fluctuations of energy and number density, and this is some low energy effective action for those fluctuations. I mean, it is still quite interesting that, from my perspective, it gives you a linear in T-specific heat. And that's not an easy thing to get. It's something that free fermions have as a linear in T-specific heat. But this kind of Schwarzschild effective action has a feature that it allows you to capture that. So now I want to come back to the first part of my talk and talk about, higher dimensional systems. And there's very nice work by Yingfei Gu et al., where they took a chain of SYK models. And here again, the key feature was that the coupling between neighboring SYK models was quartic. If you put a quadratic coupling, that's something, in fact, was studied by Georges and Parcolet. That immediately is a very strong perturbation and drives you to a Fermi liquid state. But a quartic coupling doesn't. And now you get a state, which is what, the state I've been looking for so many years. A state with strong disorder, good conduction, and no quasi-particles. And so, for example, now you can compute correlation functions in this state. So actually, I should say this particular paper looked at the Majorana limit, so there's no number density fluctuations here, but we're studying the extension. And so while the single SYK model gave you this susceptibility, thermodynamic susceptibility, what you expect in the coupled models is to get, for the same correlation functions, but as a function of momentum and frequency, the same susceptibility here, but you get this extra factor, which are the and the D is the matrix of diffusivity. So I started the talk by saying these are the quantities we want to compute, the thermoelectric coefficients, and they are related to diffusivity by this Einstein relation. And so if you solve the coupled SYK model, and for the case of energy only, that was done by Yingfei et al., you do get precisely this connection. And we're in the process of showing similar connection holes in the case of the coupled SYK models with charge density fluctuations. There's every reason to believe it does hold. And there's some very general argument that this is what should happen. Okay, so then these coupled SYK models then realize, and really I think the first solvable example of a diffusive metal with no quasi-particle excitations. There's certainly been a huge amount of work in condensed matter literature on diffusive metals, but these are always weakly disordered metals where quasi-particles are ultimately long-lived. But now we have an example where there are no quasi-particles and where there's diffusive transport of both energy and charge. Also in this paper, they computed this diffusivity, and it was related to the butterfly velocity by this particular relationship. And that particular relationship also appears in another class of holographic models that have been subject of a lot of work over the past year, especially David Waig wrote one of the key initial papers. So it turns out there is a set of very simple holographic models which don't conserve momentum. And here's one of the simplest ones. You start out with the old Einstein-Maxwell theory, which, as I told you, has this infinite conductivity, although it has many other nice features. But now you want to make the system not respect translation invariance. Now, one way to do that is to just make every coupling constant in your theory space-dependent. Well, then you have to solve the problem numerically, even when you're doing holography, and people have done a lot of work on that. But after a lot of back and forth on this issue, people realized that here's a very simple way to lose momentum conservation. You just couple the theory to what you'd call an axion field for reasons I don't fully understand. And then you take a vacuum where the axion field phi is just a constant function is a linear function of position. So that's broken translation invariance, but in kind of a soft way. It turns out that the equations you derive then are not partial differential equations, which are always hard to deal with, but ordinary differential equation, because you do have some kind of restored translation invariance. And that's good, because that's what we wanted. We want system with disorder, but with self-average. So in the end, we don't have to worry about all these replicas fluctuations. And for example, in this theory here, in the end, there's a lot of disorder, but the final equations are totally translation invariant. And that feature is also something that appears very elegantly in these axion models. Anyway, so if you now look at correlation functions in these axion models, and this is something Richard Davison has been working on, then they perfectly match these. We haven't dotted all the i's in this equation, but there's very little doubt they're going to perfectly match this particular relationship. And in fact, also you find the holographic model exactly this relationship, that the diffusion constants are related to the butterfly velocities divided by temperature. Okay, so that's kind of the summary, the end of the discussion of SYK models. So these are, to summarize, simple disordered models. And from a string theory point of view, disorder was a no-no, and I'm glad Alexei finally made it acceptable to work on disordered models. But that's here they're disordered, but in a way that the disorder just averages out, because we've banished the spin glass state. And once it averages out, you get an incoherent metal with rapid transition to chaos, and also diffusion of charge and current, of charge and energy. And the properties of these coupled SYK models match very closely to simple holographic models of this type, where you also lose momentum conservation by having this axion background. Okay, so now I want to get to the latest experiments. So this is a good time for, I have about 8 minutes, so that's good timing. Any questions on that part? All right, great. So let me now turn to a set of experiments. So this was some work I did initially with Marcus Mueller and Sean Hartnell about 7 or 8 years ago. where we started thinking about holography and then also graphene, and realized faster than others in the graphene field that there was this interesting regime of relativistic hydrodynamic transport. Of course, later on, you could really work that out without knowing about holography, but it's just a fact that in this case, the holographic inspiration gave us about a year or two lead from many other people in the field. So it was good for that anyway. So I'll talk about some of the theoretical predictions, and we were hoping, of course, right away that experiments would be done, and I contacted Philip Kim, and he started thinking about them, and 7 years later, those experiments were done, and so there was a lot of technology that had to be developed to making graphene clean enough, and to doing the measuring heat transport is not easy, but so I'll show you some of the results. So this is graphene. I'm sure everybody knows this. So it's just pure graphene here, and it has a massless Dirac spectrum of electronic excitations. There are 2 points in the Brillouin zone where the dispersion looks like a cone. These are the filled states, and those are the empty states. Now, if you take graphene with Coulomb interactions and look at its phase diagram as a function of temperature and density, then this is the rough picture. If you're at low temperatures and finite density, either positive or negative, then you have basically a Fermi surface. You fill up to some chemical potential, you have a Fermi surface, and we all know that once you have a Fermi surface in a metal with Coulomb interactions, then it's a weakly interacting system. For 2 reasons. One is the exclusion principle near the Fermi surface, and second, that the Coulomb interaction is screened by the finite density of states of the Fermi surface. So here at low enough temperatures, you expect screening and Pauli exclusion principle to make this a quasi-particle system. On the other hand, right in the middle, we argued that in fact there should be something that's almost quantum critical. First of all, there's a breakdown of screening, and then the density of states at the Fermi level, which is related, is 0. And so that means that the interactions basically are of order 1. They're of order if you estimate the strength of the interaction, they are the same order as the kinetic energy. Now, if you do the renormalization group theory, you find that the interaction, even in pure graphene, scale to 0. But they scale to 0 logarithmically. So one can hope that at some intermediate temperature range, the logarithmic flow can be ignored. So if you ignore the logarithmic flow, this is sort of like a conformal field theory in chemical potential and temperature. So it's kind of the inverse of QCD. QCD is asymptotically free at high energy. This is asymptotically free at low energies. But if you look at some intermediate regime, they're similar. So that's the idea. And so that intermediate regime is this Dirac liquid, where the dispersion is Dirac and the quasi-particles are not well defined. Now, any real system has disorder. And if you think a little bit about the effects of disorder, that tells you that you have to exclude all this low temperature regime. Roughly speaking, the idea is at low enough temperatures, where the scrambling time, let's say, becomes very long, then the scrambling time is longer than the time it takes for an electron to hit an impurity. So at low enough temperatures, the electron will hit an impurity, and it won't really have time to scramble with the other electrons, and so basically be a Fermi liquid. So you have to have temperatures high enough so that or the system clean enough that you're not in this Fermi liquid regime at low. So, but what you expect at very low temperatures, that independent of density, you should be in a quasi-particle regime. On the other hand, if you're at higher temperatures, you should see this collective flow of the whole liquid, which is the kind of thing that holography describes immediately without giving it any thought. Whereas here, you have to worry about all the Fermi surface and all that stuff. All right, so there's one very canonical way, like a smoking gun of electronic quasi-particle physics, and that's measuring the Wiedemann-Franz ratio. That's the ratio of the thermal conductivity to the electrical conductivity. And that's a pure number. It's given by fundamental constants. And basically, that's because when you have quasi-particles, each quasi-particle is carrying charge 1 and energy kT. And just from that, using the Fermi distribution, you can work out this ratio. And this is some plot we found in the literature showing you that just about every metal, when you look low enough temperature, obeys this ratio with precisely this value. So that's our smoking gun for quasi-particle physics everywhere in this regime. These are different densities. This is from carrier density from 10 to the 16th, oh no, 10 to the 24 to the, it's the same line, but it varies over huge range of densities of carriers. Okay, it's not our figure. Okay. Okay, so what is the other approach? Well, so the other approach is not individual quasi-particle scattering of impurities. It's a liquid, a quantum liquid like water flowing around impurities and obstacles. So if you take and there's different types of obstacles you can put. In this particular early theory we wrote down in 2007, we just took point-like obstacles with some density. And I showed you the formulae earlier. If you play around with those formulae, you can make specific predictions on this Lorentz ratio between of kappa over T sigma. So it's some complicated expression that does not have any quasi-particle interpretation. It has the feature that for a clean enough sample, this thing is infinity. Let's see, it's infinity at any non-zero density, and it's zero. Right, let me remember that right. I always get very confused. Okay, let's look at this. Yeah. So for at zero density, it goes to infinity. And when you make the system pure enough, at non-zero density, it goes to zero. So that's as strong an effect you can hope for. For a clean system, you want one thing to be diverging and the other thing to be going to zero. And the reason that happens is that when you are exactly particle-hole symmetric, now the thermal conductivity of any particle-hole symmetric system or relativistic system, sorry, is infinite. That's because the stress energy tensor is symmetric. Whereas the electrical conductivity is actually finite because particles and holes can collide with each other and come to rest while conserving momentum. So there's no overlap, if you wish, between the momentum and the current, or in other words, saying there's no drag of current from momentum if your chemical potential is zero. This is like this electric field term that I mentioned. On the other hand, when you're away from particle symmetry, then the thermal conductivity is finite. Well, because just like the thermal conductivity of the gas in this room is finite, thermal conductivity is always defined in the regime where current flow is zero. So there's no possibility of drag. On the other hand, electrical conductivity is infinite because there's no impurities, and then momentum will drag the current. So anyway, so you have a really very strong effect, which was buried in our paper, and we didn't really know that this was the effect to look for. But anyway, yes.
So in your work with Marcus and
Yeah.
Lars,
Yes.
you use Boltzmann theory.
Sure. Sure. Well, I mean, so you assume weak interactions, and then you can get an expression, but that expression, first of all, is extremely complicated, and it also won't show you that all these terms are in fact just related to thermodynamic quantities. There's a certain set of exact identities one can prove, which are all orders in that interaction. But it was certainly important to do all of that to check this whole formalism. Yeah. Anyway, so here's the data. So what's being plotted here is the thermal conductivity. That's the red dots as a function of density. This is the gate bar. And here and the blue line is the prediction from the electrical conductivity. So you measure the electrical conductivity, assume there's a Wiedemann-Franz ratio that predicts what the thermal conductivity should be. Then you go and measure the thermal conductivity, and as you can see, it perfectly agrees. So this is a very good test of the experiment. The numbers, the pi squared over 3 is coming right out where you expect it. And so that's this transport. So now you raise the temperature a little bit, and you start to see some deviation right near zero density. And a bit more, and you see a huge factor of 20 deviation. Exactly the way we predicted, things are blowing up right near optimal, right near zero density. All right, so that was the start. It got us all very excited. There's been much more modeling we have done, which actually I think Andy Lucas spoke about just an hour ago in the department. Here's the data for the Lorentz ratio as a function of density and temperature, and here's anyway. So at low temperatures, the Wiedemann-Franz rho is obeyed because the color is blue, and at high temperature, it's violated. And so you have this collective liquid transport, And then at even higher temperature, sorry, it's restored because of phonons. We don't fully understand that, but anyway. So we're lucky in this sample to find this intermediate regime where you could decouple the electrons from both the phonons and the impurities. And there's a number of modeling as a function of density and temperature that I guess I don't have a plot for, that Andy especially has done. There's a different model where you don't put in point-like disorder, but smooth puddle-like disorder, and that does a much better job of fitting the detailed experimental plots. Okay. And let me just close by another very beautiful experiment. Well, I shouldn't say another. A beautiful experiment by Andre Geim and others, which also is a much more direct view of hydrodynamic transport. And it's a strong contrast. It shows you clearly why ohmic transport, which is what you see in 99.9% of metals, and hydrodynamic transport are completely different, at least for weak disorder. So imagine you have a sheet of metal here, and you inject some current at this point. And you know it goes out somewhere over there. Now you can approximate the sheet of metal by a network of resistors. So I just draw a network of resistors, just a lattice of resistors, and I ask you to solve V equals IR on every resistor and figure out what the distribution of current flow is. Okay, an undergraduate physics problem, and you'll get this kind of flow. So resistor doesn't know anything about momentum. It only knows what current. So you never worry about, that's the point, and you never worry about conservation of momentum. But in a weakly disordered, like the first part of my talk, not the SYK part, the first part, where you have weak disorder, then momentum is a good quantum number for a while, anyway. And if you solve Navier-Stokes type equations, you can get, under the right regime, this kind of backflow. Basically, current flowing here is dragging the current around it, and that gives you this vortices forming. So what you then find is that if you now measure, say, the voltage, if I measure the voltage between this point and this point, here the current flowing that way, and here it's flowing backwards. And that's clearly that sign, and this is proposed by Levitov and Falkovich, is a dramatic sign for momentum drag of current. And that's exactly what they saw. So they're injecting current at this point and measuring the voltage between those two probes. This is your piece of graphene. And in the right regime, at low temperature, they see this negative voltage between those 2 points. Okay. And you can have, I think Leonid and Marco Pollini and others have a lot of detailed theory of these experiments. Yeah. Yeah. Right. Well, so this is for perfect. Now you can put in some impurities. What you really need is basically your thermal length or your butterfly length to be longer than impurity spacing. By a factor of 2 or 3, that's enough. Then there's a possibility of seeing this in the negative black flow. Yeah. So I mean, to summarize, I really talked about related but different systems. The first part I talked about the Reisner-Nordstrom black hole with weak disorder. That's what we're applying here. We're not applying SYK to the system. In SYK type models, you will not see this effect because in SYK momentum is gone. But anyway, those are still very similar systems, and now I think it's not clear yet which regime the cuprates are in. Andy McKinsey's slide seems to suggest they're not in this regime. They're more in the SYK type regime. And there's a new experiment by Aron Kopotulnik which also seems to support that conclusion, just coming out shortly. So anyway, I think experiments of this type hopefully will be done in many more materials, and we're going to learn a lot in the next few years. So I'll just conclude with my predictions. Summary. Thank you very much. Yeah. Yeah. That's right. Yeah. So maybe I said that wrong. The impurity spacing has to be longer than the electron-electron interaction time. That doesn't have the system size doesn't come into it. It's just those two ratios. Many of the calculations by Levitov have zero impurity, but you can put it in and it doesn't get rid of it immediately. So, right. Anyway, yeah, right. Yeah, yeah. Right, right. Yeah. Well, okay. So what we noted in that paper was that if you that was a slightly different model, and that spin-spin interaction. If you measured the spin correlation function, it had this log omega at small frequencies. Now, if you take that spin susceptibility and perturbatively use that to estimate some mobile electron. Imagine a condo-like model where you have some spins which are forming SYK and then some mobile electrons scattering off this SYK system, so conducting electrons otherwise. Then those electrons would have a self-energy that goes as omega log omega. So that is still a correct observation. But and the models that were studied by Georges and Parcolet were in that spirit, where they had really two systems which are weakly coupled. So I think today we need to do better. That's not a self-consistent thing. It's not as if you have two separate systems. You have to have one system which is chaotic on its own and is also conducting. That's sort of where we're moving towards. Well, that's my hope. I don't know. We don't have one yet. So what we have done some calculation the weak disorder limit, and there are some suggestive results. So I think more experiments will test those simple predictions. We'll see. And I think this new experiment of our uncoupled Toolnik is also very exciting. So we'll see where it goes. I mean, I think there's a lot to be done, and I'm optimistic. It's a long-standing problem, and I think we're finally making some progress. At least that's the way I feel. Yeah, yeah, yeah. You mean maximal meaning of order 1 over kT? Yeah. Yeah, I suspect it does. I mean, if your chaotic time is parametrically smaller than 1 over t, meaning 1 over t to the even 1 over t log t, for example, then I think there's at least you can define some logarithmically long-lived excitations whose lifetime is logarithmically longer than their energy. So which would be their quasi-particle. So usually you have something better than that. So I do think parametrically it has to be 1 over t. Yeah, the coefficient, we didn't even know how to compute the coefficient. Now with the Lyapunov definition, we can in some cases, at least approximately. Yeah, I think there is really some deep connection between absence of quasi-particles, fast scrambling, and then black holes, because these are all systems that do that.